Welcome to Physics for Entertainment, adding vectors from bee to tree. Here we have a bee filled up with nectar. It has a massive mass of, let's say 102 milligrams. So it would take about 1,000 of these bees to equal the 100-gram mass that you use for the balancing activity. So the weight of 1,000 of these bees, these honeybees, it's a heavy honeybee, on the heavy side, completely filled up with nectar. 1,000 of these put together, if they would all sit in your hand peacefully, would have the same mass as 100-gram, have the same weight in your hand as 100-gram mass. Now this bee, and that weight kind of comes into play in making some of the vectors that we'll deal with later kind of scalable, but that's actually the real weight, realistic weight for a honeybee, so it's rather nice. That means that its mass times gravity will produce a weight of 1 micronewton. So that's kind of the unit that we'll be using. So we have this bee and it's flying around, and it's flying towards the hive at a constant velocity. It wants to keep a constant velocity so that it's easy prey for birds. Well, maybe that's not such a good idea for a bee, but at this particular moment the bee wants to keep its velocity constant. It might change its velocity later, but it's decided that its velocity relative to the ground is good. And of course, we can represent a velocity vector as work with me computer, a horizontal velocity and a vertical velocity. Now, something about vectors is they work a little bit like our numbers do, in that if you can add up two things so that they're equal to another thing, then they're the same thing. Vectors work that way with addition. With multiplication they get a little bit funky, but with terms of addition they kind of work that way. So this v vector here is the same as this vy plus vx together. That's why the vy and vx are called component vectors, because both of these together give this vector. And also, like our numbers, the order that you add vectors in doesn't matter. So vy plus vx equals v, just the same as you get with vx plus vy. Either way they equal v. Though subtracting vectors can be a little bit different, but if you subtracting a vector like v minus, like vx minus vy, I'd have to flip this arrow around to really make it look like the negative vy. But subtracting vy from vx is the same as adding vx plus negative vy. There we go. So that would be negative vy. So adding vectors, they work a lot like adding integers. They have the same sort of property. Now the main reason why I added the velocity vector is just so that we have an idea of what direction the bee is going in, and so that you can kind of see that vectors all don't have to represent the same thing. That's kind of maybe about the trickiest thing to kind of get used to. But once you do, they'll make a lot more sense. And so I want to show that kind of how the velocity vector can be very different from force vectors. So this would be the weight of the bee. Whoops. moving the wrong vector around. And the x component of the weight of the b is really just nothing. And the y component is exactly equal to the weight of the b, because gravity is acting exactly in the vertical dimension. But since it's going down, the y vector is represented as negative 9.8 meters per second squared. Now the B also has a drag force. That small little U with a caret on top just kind of represents the direction, because none of these quantities really have a direction. So that's just a symbol that you might see, but nothing to worry about. And anyway, this drag vector also has can also have components. You notice that these components also add up to it, but since the drag is acting kind of against the velocity, it's not quite it has both a vertical component, a y drag, and an x drag that both have non-zero values, the x, and they're both negative. Now you might be wondering, why is this not pointing exactly the opposite direction as the velocity? And that's because this drag is v squared, so the x component has a much greater effect on the drag than the slight velocity at which the b is rising. Now we know that since the b is at this moment it's holding its velocity constant. Hard to do a constant velocity. At this moment, since the b is holding its velocity constant with the force of its wings, we know that by Newton's first law, that because it's not accelerating, the sum of the forces on it have to equal 0. Anyway, finding the sum of the total vectors, or the sum of the x components, or the sum of the y components in this case, is simple because we know that they are 0. The tricky thing that we're going to try to do is figure out how hard, and this is what the b needs to know, is if I want to keep my velocity constant, how forcefully must I flap my wings? Now the thing is that to hold constant, the b has to not only resist its mass, not its mass, its weight, but it also has to resist its drag force. So we need to come up with a vector that when we add the drag plus the weight, we need a wing force. That is a force wings that is going to bring us back to the b. Because the 0 vector looks just like a point, which means that our forces will be 0 when they all come back to where the b is. So right now, nowhere near 0. Got quite a force vector. It's going to have a negative y component that's a little bit greater than the weight of the b, and a negative x component that's exactly equal to the x component of the drag on the b. Now the way that we can find that is by starting with making a vector that goes from the tip of this vector all the way to where the first vector that we added started at. That's how we add vectors. We do find the tail of the first vector that we're going to add to the tip of the other, and then put the tail of the next vector we're going to add to the tip of the first one, and then when we get to the tip of the last vector we added, then we add the one that gets us to our final point, which in this case is right back to where we started, which is our force wings. And the force wings equals wing power divided by velocity. So if you've been looking at the set of equations on the handout, and you should download the colored handout because the vectors on it look a lot better. But it's really important to kind of translate the equations in that packet, because the concepts will really help us with combining the first, I think, what is it, about 9 chapters in the book, going from linear motion to momentum. The cool thing is that you've pretty much, like, you're dealing with a real hard thing, which is figuring out how to use vectors. But once you figure out how to use vectors, you'll be able to tie a lot of things together a lot more easily, and the rest of the course will kind of pick up and be a lot more fun. Now I'm going to remove the force wings for a moment, just to show something about vector addition. Okay, so I want to show that we can kind of add the components separately from the main vector, and we'll get exactly the same result. I mean, this is again kind of like addition with integers, that 2 plus 3 is going to be the same as 1 plus 1, which is equal to 2, and 1 plus 1 plus 1, which is equal to 3. If we add all of the components of 2 and 3 together, we'll still get 5. And the order that we do it in doesn't really matter, but it kind of can help to kind of focus on, say, one component. So start with the x. So find the x for the weight, and you notice that that doesn't really go anywhere. That's the point. And then I'll add the x for the drag. And you see that we're getting close to the sum of these two vectors. The first two vectors that we added, the drag plus the gravity. Now I'm going to add the y component of the drag and the y component of the weight. You notice that it's kind of difficult to see when they overlap like this, but they add up to exactly the same point. So now, to get our components for the x, for the force of the wings, kind of see how far in the x direction does this vector extend. And so we get that. And then for the y direction, we see how far vertically we have to go. And again, we can add the components, and it doesn't matter which order we add them in, but again I'll do add x first and then y's, just because that's often a less confusing way of doing things. It's really hard to find that x component of weight, because that is just a dot. Okay, so this time I'll start with the y velocities. I'll start with add the drag, and next I'll add the wings, and you notice each time I find I put the tail of the first vector at where I'm starting, then I add the next one by putting its tail right on the tip. So tip of the vector that you put down first to tail of the vector that you're putting down after it. And then lastly we gonna add the force of the weight. You notice that brings us right back to where we started. And with the X again, can do this in any order. Can start with the wings. You see, we're not back where we started because the X force of the wings is very significant. Now we'll add the X force of the weight. Since the weight doesn't go to the right or to the left, for the X component part, we still are exactly where we are. And finally, the X component of the drag, and that gets us right back to 0. A slightly different path. I use the B to trace out the path. So in this case, adding the Y components, I think we added the force of the wings first. What do we add? Yeah. We added the force of the wings, and then we added, oops, I need to actually, I'll pull those apart because I forgot. Okay. Yeah, so we added the drag first, and then we added the Y part of the wings. Nope. Okay, yeah. That got us up to there, and then we added the weight. So the way we added those is first the drag, then the force upwards of the wings, and then the force down of the weight. And then we added the force forward or to the right of the wings, and the force that doesn't go anywhere for the X component of the B's weight, and then the force to the left of the drag. And that gets us to exactly where we get to if we add the whole vectors. So it's just two ways of getting the same thing. Now one of the really tricky things about vectors is that like here we're using distance to kind of represent each of these vectors, but they're nothing like a distance, but a really cool ability that we have. And I've been kind of reading a lot about this over break in the book Thinking Fast and Slow by, I think, Daniel Kahneman. So what's really cool, and let me know if I'm horribly mispronouncing his name, but what's really cool that they talk about in this book is one of our awesome, really strong abilities of the components of our brain that do kind of make most of our immediate decisions at most of the time of the day when we're not even really thinking of what we're thinking. And this part of our brain is really good at relating proportions of different things, like how sweet a cookie is in comparison to maybe like how fast a car is. And those are two completely different things, but maybe you could compare like a really, really, really sweet piece of candy with a Ferrari or something like that, and you can, where it's just as sweet for a piece of candy as the Ferrari is fast for a car or something like that. Or maybe you can find like some kitten that's just as cute as say like Einstein is intelligent. It would be a pretty, or I should say, what is the word? Clever. And that'd be a really, really cute kitten. But I mean, we're really good at relating quantities that are on completely different not really directly related, but they have similar kind of proportionality to them. So that's what we're doing here. It's like here these are represented with displacements, but we're not talking about displacement, we're talking about a force, which when on balance can kind of change the rate of displacement. But whether or not we're being displaced is really has to do with the velocity here. Now let's say, like as in question 11 of the midterm, or not midterm, winter celebration, that we want to find the magnitude, or not, the value of the x and y components of the force of the bee's wings. It's like, how are we going to go about that? And also, like if we want to, like adding these component vectors is kind of really useful, but how do we find those? And now to kind of help, I'm going to put these components back real quickly on the vectors that they belong. I'll hide the x and y components for the force on the wings. So how can we calculate all of these components without necessarily having to get the exact angles and measures, and we do need to have the exact measures, but without, say, writing them out in decimal points and using all of the trig identities. How can we actually kind of do it in a more intuitive, simple way? One thing that we could do is we could put them all on a chart. So since we know that the weight of this bee is 1 micronewton, then each the side of each square represents a difference of force of 1/3 of a micronewton. So this makes, we can use this to, the neat thing about a grid is we already have it it comes with x and y coordinates built in. So once we put our vectors on it, we can very easily find out the components. As we see that the weight is going to have a y component of -1 micronewton, because that's kind of what we use. The length of this vector is kind of what we're using for our scale. So you could find the length of this vector as it appears on your screen and measure it. And then for each one of these displacements, what you would do is you'd divide it by its length and multiply that by 1 micronewton, and you could use that on any of these other displacements to actually find the form of the vector. So in this case, 1 times 1 micronewton is, well, I mean 1, whatever this distance is, divided by itself is 1 times 1 micronewton is 1 micronewton. Now to find, and that gives us the y component is going to be, since it's down, up would be plus, but since it's down it's -3 micronewtons, so that is our the y component of our weight. And the x component, well, obviously it's doesn't go either to the right or to the left, so that is 0. And then for the drag, it's going to have an x component of -1, 2, 3, 4, 4/3 of a micronewton, so about 1.3 micronewtons is the x component of the drag. And the y component is going to be about 1/3 of a micronewton and in the positive direction. So we can add that there. And then if we add both of those together to find the x component of the force of the wings, that's going to be the amount of force to counter the force to the left. So it's going to have to be 1, 2, 3, 4, 4/3 of a micronewton, so 1 and 1/3 micronewton, or 1.3 micronewtons is going to be the x component of the force from our wings, and the y component is going to be 1, 2, 3, 4. Did I count right? Yeah. I didn't realize that was square. So that also, now I know the angle here is going to be 45 degrees for the force wings. Now, if the interesting thing that's really cool is if we move those, you'll see that the x and y components add up to our vector. And if we add all of them together, then our force is neutralized, which means that we get to stay on, keep our velocity constant. So I hope you've learned a little more about how to add vectors together. They kind of, for adding, not multiplying, but adding, they work a lot like our integers. And one thing that we really have going for us as humans is that we're good at comparing things that are very different from each other, such as cleverness and cuteness, but we can still compare the extremes. So we can use the same sort of object, a metaphorical object, to describe things as different as velocity and force, which, as you can see from this equation here, force equals power divided by velocity. It tells you how we can actually combine all of these together. If we multiply velocity on both sides, we have that force times velocity is power, which times time is energy, which gets us one step closer to getting into the subject for the next semester of conservation of energy, which will actually probably come to maybe a little bit in the next week and a half. We'll definitely be hitting momentum, which is a very close subject. So until next time, enjoy physics.